Hi everyone, my name is Neha and this is the 12th lecture on electronic communications. In this lecture we are going to learn about wave propagation. I hope you remember in the last lecture we covered the antennas and this is the second part of that lecture. So let's get started. Wave propagation. So when a radio wave is generated at a transmitting antenna, it begins its journey to the receiver. And in between you know that the wave travels, and when the wave travels, that is called your propagation. So propagation is actually the process of wave movement, and in radio wave it propagates a similar manner to the light waves, which is higher frequency electromagnetic energy, and the frequency of the visible light is 4 cross 10 raised to the power 14 hertz, whereas for highest radio frequency it is close to 100 gigahertz. So because of their frequency difference, there are some important differences in how these two types of electromagnetic energies they travel through the they travels. Uh, so that is what something we are going to learn in this lecture. Now I'm going to quickly read these 2 points, and let's see here. Waves from antennas may propagate by direct line of sight, which is phase wave. And then we have ground wave or ionospheric refraction, and above high frequency ionospheric propagation becomes rare. So all these different propagation modes we are going to see in this lecture. And then we have link budget, which is used to quantify the performance of a complete transmission system, including transmitter, receiver, antennas, and the surrounding environment. So this is also we are going to cover up in this lecture. So we have here how radio waves changes its direction. So the radio wave, you know that it travels point to point. They often moves in path that are not straight line. And there are 3 mechanisms that can change the course of radio waves. And those are reflection, refraction, and diffraction. And in real life, all these actions take place for any given radio signal. So in reflection, when radio waves it strikes on this conducting surface, then it bounces off the surface in the same manner as the light reflects from a mirror. And when a wave reflects, then it produces the angles, and this angle is called your angle of reflection, and this angle is called your angle of incidence. And in reflection, these 2 angles must be equal. And this is the conducting surface, and that which is the condition for the reflection. You need to have a conducting surface, then only this reflection action can take place. Now second is the refraction. In refraction, you have 2 mediums, medium 1 and this is medium 2, and they both have different index of refraction. So what happens when the radio wave is incident on the medium, and it travels from one medium to another by the refraction. So here you see the ray is basically bent at a inference of these two different materials, and goes into the another medium. And in this refraction, it has a critical angle. So first this angle is the angle of incidence, and here this big angle you see is called the critical angle. So any radio wave which is entering beyond this critical angle. So for example, from here you see this this wave which is entering over here has an angle greater than this critical angle. Then what will happen? The ray will actually reflect. So in this we understand that if any ray is having a greater angle than the critical, then the ray will reflect. Otherwise the ray will refract and goes into the second medium. And this critical angle will be equal to the inverse sine of n2 by n1, where n2 and n1 are the index of refraction. Now next is diffraction. In diffraction, the radio wave is incident on a opaque material, and opaque material could be anything, for example buildings, mountains, and in that case when the radio waves is incident, then the diffraction of then the rays will be diffracted, and these diffracted rays will be much weaker than the energy in the main portion of the radio wave, but these still can be usable in many cases. So this was your diffraction, and now I'm going to move to three propagation modes. And you know that a radio wave can make it from transmitter to receiver by one of the three signal paths, and these are called first is called your direct or space wave path, second is called your ground wave path, and third is called your sky wave path. So the direct or a space wave path, it works on the frequency 30 megahertz and above, and that frequency is called your ultra high frequency or very high frequency. And whereas the ground wave path, it works on frequency from 30 kilohertz to 3 megahertz, and the sky wave path works in between 3 megahertz to 30 megahertz. So as you know that in a radio wave, it may have to be reflected or refracted or diffracted as it follows each of these paths. And if a radio wave follows two or more paths, then what will happen? The result will be your multi-path interference, and that multi-path interference we are going to see next. Now let's first discuss the direct or space wave path. In the direct or space wave path, it is the radio wave that travels in a straight line between the transmitter and the receiver. So let's assume this is the transmitter, this is the receiver, and you can see how straight the radio wave is traveling. In this type of wave path, there will be no bending of the wave, and it is also known as line of sight communication, the name of this type of wave path, and it is used in satellite communication and for the short distance communication on the surface of the earth, and the example for that would be FM broadcasting. And if you see here, the two station, they can see the same they can see the same radio horizon. So this is called your radio horizon, which depends upon the antenna heights, and they can communicate using the space wave. So this is your space wave, and here if you want to calculate the distance to radio horizon for each station, you can calculate it by using this formula, which says d is the distance in miles is equals to under root 2 h. H is the height in feet. So you can calculate the distance. So for example, if you want to calculate the d1 distance, so you will write here d1 is equals to under root 2 h1, and that will give you the answer if you know the height of the antenna. So in this equation, but you have to assume that the Earth's surface is smooth and no object are blocking the radio signal between the two stations. Now next is the ground wave. And ground wave works for a low frequency. You can see here 30 kilohertz to 3 megahertz, and in this type of wave, a portion of the radio wave energy will tend to follow the curvature of the earth for a distance of approximately 100 miles and providing a reliable communications. This type of ground wave path is used for amateur radio system and in military communications at a 1.8 megahertz of frequency. The ground wave propagation, it depends on Earth's conductivity, which varies from region to region. For example, in water or in salt water, the conductivity is very good, whereas if we see the dry ground or a rocky ground, the wave propagation will not be that good because the conductivity is not that good in that case. And in order to propagate efficiently in ground wave path, the ground wave component of the radio signal, it must be vertically polarized. And the reason for that is when a horizontal wave, if you have a horizontal polarization, then its electric field component will be parallel to the Earth's conductivity, and the Earth tends to short out the electric field of a horizontally polarized ground wave, and that's why these ground wave component of the radio signal, they must be vertically polarized in order to have a good propagation from transmitter to the receiver. Now next is the skywave path, which works on frequency 3 megahertz to 30 megahertz, and we are going to see that through this example picture. And here you see this is the Earth's surface, and this is the station 1, and this is the station 2, and you see that a signal is being transmitted, and some portion of the signal is going into this another medium, where this portion is your ionospheric layer, and this ionospheric layer is basically the region of atmosphere that is electrically charged. And this layer of atmosphere is not very dense, and it results in the electrons and holes which are able to move about for some times before they recombine into the neutral atom. And you can see here in this picture that different layers of atmosphere has been shown. So you have Earth here, and then you have troposphere, and then these are the different atmospheric layers which are mentioned at different distance. And above all these atmospheric layers, you have this ionospheric layer, and this is the same ionospheric layer. And this ionospheric layer has a different refraction of index than atmospheric layers below it, and therefore it can bend radio waves back towards the Earth. So that's what you see here, that some of the signal, when it reaches to the ionospheric layer, it is refracted back to the Earth. And for radio signal to be refracted successfully back to the Earth, it must approach to this ionospheric layer at or less than the critical angle. So you see here, this is the critical angle, so it should at least reach to this critical angle, or it should be or less than the critical angle, and then only it will be refracted. If the signal is greater than the critical angle, then what will happen? Then rays, you see, it will enter, if it is more than the critical angle, then it will pass through the ionosphere. Now here, this interesting thing to note is that if the critical angle is held constant and the radio wave frequency is increased further, then no wave will be returned to the Earth. In that case, there will be no wave which will return to the Earth. And here the highest frequency that can be refracted for a given path, it is called your maximum usable frequency, and the short form of that is MUF, maximum usable frequency. And when communicating by skywave, the highest usable frequency basically provides the best received signal strength. Now these ionospheric layer, they tend to absorb longer wavelength signals and let the shorter wavelength pass. Therefore, the most efficient frequency of or any particular path is one just below the maximum usable frequency. Now here, refraction we have already covered. Let's understand what is skip zone. As you know, in the transmitting station signal, sometimes the signal is not audible in all the locations when the signal is being transmitted at the receiver side. Not always it is a case that you will be able to listen to the signals. So as the receiver, this receiver moves away from the transmitter, it eventually gets out of the range of the ground wave. and it depends upon the antenna height, terrain, and other operating frequency, and this distance could range from a few miles to maybe over 100 miles. So once out of the range of the ground wave, then what will happen? Then no signal will be received from the transmitter, and the receiver in that situation will be in the skip zone, where there will be no signal received. However, as the receiver moves further, so for example, the receiver was here and you're not able to you are not able to listen to the signal. However, if the receiver, it moves further from the transmitter, it eventually moves closer to the location where the wave has returned from the ionospheric layer. So at that point, the receiver again detects a strong signal. So you can see this is the skip zone, and here, and secondly here, if you have a station over here, you can listen to the signal, and here we have a station. So here the station will be able to listen to the transmitting signal. Now let's move on to the next slide. Next we have tropospheric ducting. So this tropospheric propagation describes electromagnetic propagation in relation to the troposphere. It is often observed on the very high frequency and ultra high frequency bands. So in the troposphere, a duct is basically a portion of a low atmosphere that has ability to carry a radio signal for a long distance. And in unusual weathers, such as when there is a temperature inversion, then they are usually responsible for the formation of the duct. And once radio signal enters that duct, it is actually trapped between the air layers by refraction and travels very efficiently to its destination. Now next here we have the multipath interference. It occurs when a radio frequency signal from a transmitter arrives at a receiver via two or more routes. So they typically, there is a direct path plus a number of indirect paths that's caused by the reflections, and walls, people, and set pieces and other objects in a room can cause reflections indoor also. So these radio signal, they can reach the receiver in many ways. So here in a figure, it shows two versions of radio signals reaching the receiver. So here is your transmitter and this is your receiver. And there are two ways the signal is being reached to the receiver. First is this direct wave, which is coming from transmitter and going into the receiver. And the second case is when the wave is reflected back from this building, and then after reflection, it is going to the receiver. So these are the two different cases, and in the second case we see that if the signal reaches the receiver antenna in phases like this and after this, then the constructive interference will take place here, and the receiver, it may experience a stronger signal than normal, or there may be the cases when the reflected and the direct wave, they totally basically cancels out and leaving a dead spot. And the example of this would be when a vehicle is moving, then you might have observed that there is a appearance of a signal which is like very distorted, and sometimes you see there is no signal received at that particular frequency. And also in the analog television, sometimes it used to happen that there is an appearance on the ghost like screen gets freezes. So those are the example of multipath interference. And another example would be in the digital TV, which shows periodic dropout of picture data occurring every few seconds. Now moving on to the next slide. Next is the link budget. So link budget, it is an accounting of all the gains and losses from the transmitter through the medium, which is our free space, cable or waveguide, or it could be fiber optics, to the receiver in a telecommunication system. And it is a important goal of a communication system to provide the reliability over a specified distance. Now, to establish a communication link between the transmitter and receiver, your receiver must be strong enough to receive a signal, and that signal should be of that capability that it should avoid any kind of noise which is coming from in between the transmitter and the receiver. So that minimum signal must be established between the transmitter and the receiver should be capable enough to receive that signal, and it should be strong enough to avoid any kind of noise. Then only the communication will be established between the transmitter and the receiver. And the receiver manufacturer, they normally specify the sensitivity of the receivers either as an antenna circuit voltage or power needed to be obtained as stated in the bit error rate for digital data receiver, or signal to noise ratio for a analog receiver. And now here, the factors that influence the receiver power level, they include like transmitted power, transmission line losses, transmitted antenna gain, free space path loss, path obstruction, receiver antenna gain, etc. And here you see FSPL. It is basically the free space path loss, and it is actually the amount of signal lost between the transmitter and the receiver. It depends on the frequency and the distance between the device, and it is given by this formula where FSPL in dB is equals to 32.4 plus 20 log D plus 20 log F, where D is the distance in kilometers and F is the frequency in megahertz. Now let's see next. Next is the link margin, and it says link margin, it gives the minimum transmit power needed to achieve the connectivity goal of the system. So let's see some example problem based on this. What is the ideal required transmitter power of the following system? The parameters are as follows. Frequency is 450 megahertz, and distance is 50 kilometer. Receiver power level needs to be at least negative 100 dB, and we have transmit antenna gain which is plus 6 dBi, and receiver antenna gain is plus 3 dBi. Assume that transmission line losses are negligible, and not a realistic assumption, but this simplifies the problem. Express the transmit power in dB and in watts. So this is actually the solution to the problem you saw in the last slide, and you will be using this formula FSPL, which says this, and you will put the value of distance and the frequency. So we know that the distance here is 50 kilometer and the frequency is 450 megahertz. So you will put that value and you will get a free space path loss, which is here 119.44 dB. Now we need to calculate the total gain. So to calculate the total gain, we need all these three factors: transmitter antenna gain, and path loss, which is this, and the receiver's antenna gain. So I'll quickly go back to the this figure. If you remember, here we have GT. This is the transmitter gain, this is the receiver gain, and then the loss in the path. And if we add all these three together, we will get the total gain, and that's what we have done here. Transmitter gain is already given in the problem, which is 6 dBi, and the receiver antenna gain is given 3 dBi. So we have put these two values, and 119.44 path loss we have already obtained. So we will add these three values, but here make sure this is a path loss. So this path loss, this must be basically subtracted from these two gains. So here you obtain the total gain 6 dB minus 119.44 plus 3 dB, and you will get negative of 110.44 dB, and that is your total gain. So now to calculate the power at the receiver side, it will be equal to the power at the transmitter side plus the total gain. So you will use this formula, and let's read here. Remember that everything is in the dB units, so we add and subtract to get the result, and by arranging this equation you will get PTX, which is the transmitter power, is equals to receiver's powers negative sign, and then we have total gain. So when you subtract these two values, PRX, let's see at the back what's given here. So the receiver power level needs to be at least negative dB, so it is already given. We will put the value negative 100 dB, and we will get positive 10.44 dB power transmitted. So now, since this is in dBi, and if you want to convert it into watts, you will use this formula 10 log P by 1 milliwatt, and then after conversion you will get 11 milliwatt. So a transmitted power of at least 11 milliwatt is needed to get the desired power level at the receiver, at least under ideal conditions. So this was a small problem based on budget link and link margin. Now let's go to the summary of the whole lecture. So I'll just quickly read all the points. It says propagation is the movement of radio waves from point to point. Radio waves can change direction in their course of travel by reflection, refraction, and diffraction. And I hope you remember there were three propagation modes which we studied. First was the space wave path, second was the ground wave, and the third was the sky wave. Now let's see next. In a link budget, it is important to know the distance and the maximum power allowed by the FCC rules, the frequency and the types of antennas being used. It's also useful to know about the environment so that an appropriate fading model can be used. Link margins are used to assure a certain level of link reliability in the presence of fading, a common feature of terrestrial links. So this was the summary of the lecture. Thank you so much for watching.